Okay, just a couple of other things to finish up this in phase bit. So 2 points are in phase with each other if they are the same distance from the rest position, on the same side of the rest position or equilibrium position, and moving in the same direction. So this point here and this point here are in phase because they're the same distance, on the same size, moving in the same direction. B would not be in phase with them because it's moving in the opposite direction. These two are about to move up, B is about to move down. Okay? Now, when they're in phase, then they're going to be a wavelength or a whole number of wavelengths apart. And we say one wavelength is 360 degrees. I want to show you why. You may have seen it in math, but maybe not. So if you have your calculator, pick it up, and if you don't, pause me and go find it. Because what we're about to do is plot a sine wave. So I'd like you, in degrees, with your calculator, find the sine of 0. And it should be 0. Now find the sine of 45. And you should get 0.707. Find the sine of 90 for me. It should be 1. The sine of 135. You should get 0.707 again. The sine of 180 should be 0. The sine of 225 should be 0.707 again. The sine of 270 should be -1. The sine of 315, -0.707. That last one was negative as well. And the sine of 360, you're back to 0. If you now plot the points, connect the points that we just plotted, you will see it's a wave. This is known as the sine wave. Okay? And so we say one wave is 360 degrees. So 2 points that are in phase with each other are 360 degrees apart. And 2 points that are completely out of phase with each other, like this guy and this guy, that's a half wavelength. They'd be 180 degrees apart. Okay, and so the wave we've drawn here is really a one-dimensional wave. But if you're in your bathtub, or at least sitting on the floor of your bathroom and playing in the bathtub, the waves you're going to be creating are two-dimensional. And if you were in a swimming pool underwater, they could be three-dimensional. These lines that I'm drawing that you see in the water, these lines are called wave fronts. And really, they're like on a wave front, all the points on that wave would be in phase. So imagine them as a whole bunch of one-dimensional waves, right? Going down, up, there's the crest, down, up, there's the next crest, down, up, there's the next crest. There are a whole bunch of one-dimensional waves that are in phase with each other and therefore create crests, right? So all along here, these are one-dimensional waves coming out that are all in phase with each other, okay? So that's really all a wave front is. While I was waiting for that last video to upload, I realized I forgot to say a couple of things about frequency. If you go back to the notes that I had posted for you, I have here that frequency in sound is what? And those of you who are musicians, you would probably know this. When you change the frequency of the sound, what are you changing? Gee, I don't know. What am I changing? I think I'm changing the pitch. Right? So the frequency of the sound is the pitch of the sound. The frequency of light, when you change the frequency of light, what are you changing? It's the color. Okay, so I forgot to say that. And the other thing I forgot to say was, what is it that determines the frequency of a wave? Well, if we go back to your water wave here, what determines the frequency of your wave is how quickly or how slowly you're moving your fingers. So what determines the frequency of any wave is its source. If I want to make my frequency higher, if it's a sound wave, I want a higher pitch, I need to vibrate my vocal cords faster. And if I want a lower pitch, I can't do it. I need to vibrate my local vocal cords slower. Okay, so the frequency of the source determines the frequency of the wave, and once the wave leaves the source, the frequency can't change anymore. The speed might if it goes from one medium to another, but the frequency can't. So if the speed changes going from one medium to another, it's going to be the wavelength that will change, because the frequency can only change at the source. It can't change once it's left the source. Okay, so today you're going to do a few questions with a few of our new equations and one of our old equations. So one of the equations you will need is your old friend, good buddy, and this is if you have the distance the wave is traveling. You also need the universal wave equation, one of our new ones, V equals F lambda, and then you need your frequency and period ones. Okay? And we'll come back next day and learn some more about waves.